This video covers abstract data types. It's topic 10.4 on the CIE 9618 specification, and it's the last part of section 10. So what we need to do is be able to define abstract data types, understand that they're a collection of data and the operations that take place on the data. We need to be able to identify abstract data types, including stacks, queues, and linked lists. We need to be able to describe the key features of each of those and justify which one we would use in a given situation. And we need to be able to describe how we store data in them, how we add, edit, and delete data from those different abstract data types. We don't need for this part to be able to write pseudocode to do that. And we need to be able to implement these with arrays, i.e. describe how they would be implemented with arrays. So what is an abstract data type? It's a collection of data and the set of operations on that data. So the data is defined by what you can do to it, not how it's stored in memory. So we have two parts: the interface, which is what it is, so this is how we use it, the set of operations available to the users of the abstract data type. So within your code, how would you be able to use it? What operations can you do? So for example, you could be able to add to it, remove from it, and check if it's empty. And the abstract data type definition guarantees those operations, and the operation stays the same regardless of how it's actually implemented underneath. And then we have the implementation, which is how it's actually implemented. So the actual data structure that's used underneath the abstract data type. And usually, in this course at least, that's a fixed size array. Because pseudocode, for example, the definition of pseudocode arrays are their fixed size data structures of a single data type. And that's how we usually implement these three. There are other ways, but we don't need to look at those a lot. And the actual implementation is hidden from the user or from the code that you're calling it with. You don't need to understand how it's implemented, you just need to know how to use it, how to call it. And that implementation could change at any time, and it should have no effect on the actual use of the abstract data type. So it could be an array, and then at some point you change it to another data structure or another way of implementing it, and the code that uses it should be able to stay exactly the same. So the abstract data types we have on this course, in the AES part at least, are stacks, queues, and linked lists. So a stack is called a LIFO, that means last in, first out. So items that are added and removed are done so from the same end, which is the top of the stack. You can imagine this like a pile of plates, and if you were going to take a plate from the stack of plates, you take it off the top. If you took one and you realize you didn't need it, you would probably put it back on the top of the stack of plates. So that's how a stack works. And then we have queues. A queue is called a FIFO. It's a first in, first out. So items join at the rear of the queue and they leave from the front. So just like a queue of people queuing up at a counter to buy something, like a coffee, they queue up and the person at the front gets dealt with first. And if you want to join the queue, you join at the end of the queue. And then we have linked lists. Linked lists is a sequence of nodes, but each node holds a pointer to the next item. So the order of the nodes doesn't actually depend on where they're stored, either in an array or in memory. It doesn't matter where they are physically stored. The pointers tell you the order of the items in the linked list. So let's look at a stack a little bit more. As we said, it's a last in, first out type of data structure. We have something called the top, and the top, it marks or points to the item that we consider to be at the top of the stack. And then there's a base of the stack at the other end. Okay. So we have operations on this abstract data type, and they're push, pop. Sometimes we have a peek, and we have is empty and is full. Push adds a new item of data onto the top of the stack. So if these are all the same kind of thing, like numbers, we will be able to push another number on top of the stack, and they have one more number on the stack. Pop does the opposite. It removes something from the top of the stack. So wherever top points to at the moment, when we pop, then that's the one that we will take off. And then we'll have to adjust the top so that it moves down one. And peek is a way of looking at the item on the top of the stack without actually removing it. So it's just checking it to see what it is, but we're not taking it off. And is empty and is full are there to see if the stack is actually full. Now this depends partly on the underlying implementation. So if we were to implement this with an array, then because arrays are defined as fixed size data structures, there's a possibility that they will become full. So if we keep adding and adding, at some point we're going to have too many items and the thing is going to be full. So we need to be able to check that so that we don't try and put another item on when it's already full. And we also need to know when it's empty, because if we try and pop an item off the stack and it's empty, then things are going to go wrong. It doesn't work. So we need to know before we try and pop an item, is the stack empty or not? So why would we use a stack? So stacks are good when we want things to be taken off that were most recently added. So for example, if we're doing an undo and redo function in a software package, like undo and edit and then redo the edit, then this suits a stack. So each action is pushed on and then undo pops the most recent one off. So we can keep undo, okay, of all the actions that we put onto the stack, so we can undo them. And we can actually similarly do a stack for redoing items as well, so we can get back to where we started from. Things like function call management, so the stack can store the return addresses. So if we repeatedly call functions, then we can keep track of what happened just before we called this function, so we get back to the most recent thing before that function call, and before that, and so on. We can use stacks to reverse data. We can push them all on and then pop them all off, and then they'll be in the opposite order to where they started. And it's used for things like balancing brackets in code when you're compiling code. So every time you open a bracket in a line, a statement, then it'll push onto the stack. And then every time you close a bracket, it will pop it off. And if they match, then you'll end up with nothing left on the stack. If they don't match, there'll be something left on the stack. So, as we said, stacks can be implemented with arrays, and an array is a fixed size data structure. So we can put data in, but we would need a pointer to indicate where the top is. So in this case, we have a 0 indexed array, and 0, 1, and 2 are occupied, they have data in them, and we consider that the top is at position 2, index value of 2. And if we're popping items on, first thing we do is check if the array is full or not. If it's not full, we increase the top by 1. If it is full, we're going to return something that indicates that the stack is full, right? So we don't carry on and try and continue processing when we're unable to put something onto the stack. So we increase the top value, this top pointer, which is just a variable that indicates the index of the top of the stack, by 1. And then we place the data that we want to put at that new location. So in this example, if we wanted to add another letter into the stack, say E, we would increment the top to make 3, and then put our E value into the array element at position 3, and then top would equal 3 now. And pop, similar in reverse. First thing we do is check if it's empty. If it's empty, there's no point in trying to pop. So again, our pop function would need to return something to indicate that the stack is empty. Then we read the value at the current top. So in this case, if we were reading the current top is 2, and so we read that and we get a C back. And then we decrease top by 1. Okay, so top would become 1 instead of 2. Now, it's useful to note that the C does not disappear, it's not deleted, nothing happens to it at this point in time. All that we do is change the top value, the top pointer, so that it no longer points at that value. Okay, so top becomes 1. The C is still there, but we don't treat it as the top of the stack anymore because the top variable is now pointing at 1 instead. And at that point we can return the value from the pop function. So now let's look at queues. Like I said, a queue works like a real life queue with people queuing up for something. Think items leave from the front of the queue. They always leave from the front, and they always join at the rear. You're not allowed to insert something into the middle of a queue. So it's simpler. It always leaves from the front and always joins at the rear. Remember, it's a first in, first out data structure. Items are removed in the same order they arrive. And the functions we have are things like enqueue, dequeue, and isEmpty and isFull again. So enqueue just means to add to the queue. So we add a new item at the rear, that's enqueuing. And dequeue means to remove an item from the front of the queue. And again, isEmpty and isFull you need because the queue could get full. Again, if it's implemented in an array, a fixed size array, it's possible that a queue could get completely full. And you may have nothing in the queue, in which case queue is empty, and you need to know those things. So when would you use a queue? Queues are used when we want things to be fair, you want things to take turns of things, things have to be handled in the order they arrive. Print queues are often done like this, so documents print in the order that they were sent to the printer. It's considered fair. CPU tasks get scheduled in this way sometimes. So again, to be fair, to give processes time on the CPU, then they might be done in a first come first serve basis. So they go into a task queue. Data can be buffered like this. So when you're typing on the keyboard or streaming data, then you want them to be dealt with in the order they arrived. So if you type a word in, then it gets processed in the same order when it's ready to process them, and the letters don't get muddled up. We also simulate real-world situations like this, so helplines, tickets, checkout simulation. This would use queues. Now we can implement queues in a number of different ways. A simple way of doing it would be to just have a linear array, and you put the items in the queue in whatever position that they arrive in. So in this situation here, we've currently got the front of the queue at position 1, not 0, and the end of the queue, the rear of the queue, at position 3. And if something gets added, it will go into position 4, and if something's removed, it would be removed from position 1, and then the front would become 2. Now, the slot there, for example, at 0, has been dequeued in the past already, and that slot's wasted. It doesn't get reused in this particular implementation. Now, you could move everything along every time something is removed from the queue. Just like in real life, queuing up at a counter, one person gets dealt with, they go away, and everybody else takes a step forward, and they shuffle forward a little bit. So we're not wasting the space at the front of the queue. However, in this approach to a linear queue implementation, then space gets wasted at the front. And it's quite likely that over time we will drift along the array and then get to the end of the array and be stuck. So that it's quite likely that over time that we'll drift in the array and get towards the end of the array and then run out of space to use. So anyway, operations would be NQ and DQ. NQ is you want to check to see if you haven't got to the end of the queue, i.e. you've used up all the space. Even though you're wasting some of the space, you still have to detect whether it gets full. So you increase the rear by 1, so move that from say 3 to 4, and then you place your item at that position. In this case it would be array 4 would get populated next. And then the opposite for DQ, you check the front has not passed the rear. If you were to get say a front of 4 and a rear of 3, that means there's nothing in the queue. Okay, you've DQ'd everything, and then you realize that there's nothing left in the queue that way. If it's not empty, you can read the value at the front, and then increase the front by 1, so you move it along. So you don't do anything with the value that's left there in B, where it is in position 1. You take the B out, and then you just move front along to position 2. The data still stays in the array, doesn't need to be deleted or overwritten or anything like that, because your front pointer moves to tell you where the front now is. Now, a better way of implementing this is with a circular queue. Again, we have a front and a rear of the queue. We're trying to get around this problem of wasting the space and drifting along the array until we get to the end of the array and then run out of space. So what we do in a circular queue is we wrap around. So when we get to the end of the array, then we go back round to the beginning of the array. So to do that, we need a little bit of maths to work out what the index value should be in the array. It's a little bit more complicated than just the linear queue. In a linear queue, you can just add 1 to the rear when you want to add one, for example. In this case, in a circular queue, we can't just add 1 because eventually that will fall off the end of the array, and we want to go back round and use the one at the beginning of the array. So what we do is we say the new rear point is the rear plus 1, but then mod by the array size. So that means divide whatever number we get when we add 1 to the rear by the total size of the array and find the remainder. So if in this case we have, let's see, 6 items in there, if we were to say we're already at the last one, which is 6, let's say it's a 1 indexed array in this case. So we go, it's 1, 2, 3, 4, 5, 6. So the index value for the last one is 6. If we were to try and increment that by 1 to put a new one in, we'd get 7. Now 7's not okay. It's not a valid index value. We want it to go back to 1. So what we do is we say 6 plus 1, which is 7, and then 7 mod array size, which is 6 in this case, and 7 mod 6 equals 1. So then we come back to the first position in the array, which is index value 1 in this example. So again, we've got the same sort of thing, NQs and DQs though. We do the same when we're NQing, we check the queue isn't full before we try. If it isn't full, we can go ahead and work out the new rear and then put the value in as normal, the same as with the linear queue. The only real difference is how we work out what the rear value should be. Similarly for DQ, we have to check if it's not empty first of all. We can't DQ something if the whole thing is empty. We read the value at the front, whatever the front points to, and again, once we've removed that, we have to work out what the new front should be. And again, the front may need to go wrap around and go back to the beginning. So again, we use the mod method to do that. Now we have a linked list, and a linked list is considered as a series of nodes. And each node consists of a data part and a pointer. And the pointer points to whatever the next node in the order is. Okay, so it doesn't have to be the next node in the array or the next location in the array. It could be anywhere in the array, but it's considered to be the next ordered item, so the next logical item that you want to get to. So we always need a start pointer, which is a place to begin the whole chain from. So that's usually called the start pointer. And then each node has a data and a pointer to the next one. Now the very last one in the chain, you see has a value of m there, has a null pointer. And there's various ways of indicating what that would be. In exam notation, they often use that 0 with a cross through it to indicate null. Or you can say things like -1 to indicate that it's an invalid pointer, so it's not pointing at anything. Now what's this do? This allows us to have non-contiguous storage. That means we don't need to store the data in the same order as we want to process it in. It can be in any order physically, but we know the order by following the pointers. You can make these to be dynamic in size to allow them to grow and shrink by one node at a time, just as you need it. Obviously, it partly depends on the implementation, but if these pointers were actually just pointing to locations in memory, when we can keep adding and adding and essentially until memory runs out, whereas with an array we would be more constrained. And it's also an efficient way of inserting or deleting data from an ordered list of items. So we don't have to move items around within memory when we want to insert a new item or delete an item. All we have to do is adjust some of the pointers to go around it. For example, if we're deleting one, we can just bypass it by changing the pointer so that the previous item is no longer pointing at it, but it points around it to whatever the deleted item is pointed to. And the same for insertion. We can insert wherever we want. We just need to make the previous item point to it, and then it point to the next one that was in the sequence already. But you do have to process these sequentially. So you have to start at the beginning, and it's called traversing. So you have to follow the links all the way through to get to where you want to get to. You can't jump immediately in like you can with arrays. Okay, so it does take longer to get to where you want to within the linked list. So where would you choose a linked list? If your data size is changing quite a lot and it's unpredictable as how big or small you need it to be, then linked lists are a good choice if you can implement them with memory locations. If you're frequently inserting and deleting items, then it's more efficient because you don't have to move the data around like you would with something like an array. You can maintain an order with this. So there's a very explicit order of items within a linked list. You follow from the start and follow the pointers wherever they tell you to go, and that is the order that the data should be in. And you can use these to implement other kinds of data structures like stacks, queues, trees and graphs and so on. So where you've got these dynamic data structures, for example, stacks, you may not know how big your stack's going to get. Like it could get very, very large or be very small. So you might want to use linked lists. Same for queues. You might have print queues, for example, and it's very hard to predict how many people are going to try and print at the same time. So a linked list would be beneficial in that sort of situation. All right, let's take a look at how we can implement a linked list with arrays. So our pointers in our nodes are now effectively just array indices. And in an array, we can hold more than one list at a time. So in this example, what we're doing is we're storing a free list, which is a list of all the nodes that are available to use, and the actual linked list itself. So we have a couple of pointers. The first pointer is a free list pointer, and that points at the first one that's not being used. At the very beginning of this process, the free pointer would start at index 0, and every single node would be empty. So every single node would just point to the next node they'd all be in a free list, and the last node would have a next pointer of -1. Once we start adding data, we're actually going to reuse free nodes and put them into the other linked list, which is in the array, which starts at the location indicated by the start pointer. So now we have two beginnings, if you like. We have the start of the free list, which is the free list pointer, and the start of the actual data list, which is called the start pointer. And it's perfectly fine to have two or even more linked lists within a single array, because they can start anywhere, and all we do is follow the links until we get to a next pointer of -1, and we know that's the end of that particular list. So it's really a very interesting and useful kind of data structure. You can hold multiple things at the same time. But in our implementation here, we're just storing free nodes and used nodes in these two separate linked lists. So in the example, the free list currently points to the beginning at index 1. It's got no data in it, and it points to 3. And then 3 has no data in it, and -1 as the next pointer. So we currently have two free nodes in our free node list, and everything else is in the used list. So the start of that used list, our normal linked list that we're interested in, is at location 2, and that contains value b, and then that points us to 0. Note that it's not doesn't have to be ascending, it's actually going backwards in the array. That's perfectly fine. We just follow the pointers to wherever they need to go. So we go back to 0, that's got an f in it, and that points to 4. We go to 4, it's got k in it, and that points to 5. We go to 5, that's got m in it, and it's got -1 as the next pointer. And that tells us that's finished, that linked list is over, or at the end, we can't go any further. So the order of our data in that linked list is BFKM. So if we want to insert a node into this, then first of all what we need to do is find where the next free node is, which is indicated by the free list pointer. So we take that slot, we use that one. So if we were adding a new one in this example, we'd be going into index location number 1, and we'd be reusing that one. So we'd write our data in there into index position 1 where it says data, and then we've got to repoint the previous nodes next to the new slot. So whatever our previous one is, which is currently 5, so we've got at this moment 5m -1. If that was our previous node and we wanted to add one after m, then we would need to put the new value in the index location 1. We would need to change the pointer. If it's going at the end of the list, we change the pointer to -1, and we change 5's pointer so that it points to location 1 instead of saying -1. So in that way we've added an item onto the end of this linked list. If you want to insert it in the middle, it's fine, we can do that. We just need to find where we want to put it and then update the nodes accordingly. So again, the free item would be used, the free node would be used, that would be taken off the free list. The free pointer has to point to the next free one, i.e. the one that it used to point to. So in the case where that node at location 1 gets used, it's currently pointing to 3. Once that one's used, we have to change the free pointer so it no longer points at 1, it points to 3. And deleting a node is similar. We have to traverse the linked list to find the node we're intending to delete, and then we have to remember the previous node's next pointer so that we can adjust things accordingly, and we set the free list pointer to the released node's address. So let's look at how we choose the right abstract data type. First of all, we can look at how the order is handled, and in stack it's last in, first out, queue, first in, first out, and linked list, whatever order the pointers define. So we can see the order of a linked list by following the links. And access points, the stack, you always go to the top, you access the top. Queue, you access the front and the rear, not the middle. And linked list, you start from the beginning based on your list pointer, and you traverse, follow it through from pointer to pointer, all the way from the start until you get to where you want to. In terms of whether they can grow or shrink, then stacks grow and shrink, but within a fixed size array, if that's how they're implemented. Similarly for queue, and linked lists, then you can expand them one node at a time. If you're implementing it via memory locations, then you can just add more and more and more. You're not constrained by the size of an array. Obviously, if you do implement it with an array, then you are constrained again. Typical use, so stacks for things like the undo history or a call stack. Queues for things like print queues and task scheduling. And linked lists for things that change a lot, i.e. dynamic lists, and if you want to do a sorted insertion efficiently. So some common mistakes people make, mixing up LIFO and FIFO, so try and get those the right way around for the right data type. Sometimes people refer to a stack or queue as an array or assume an array implementation. So they are two different things. The actual data type and how they're implemented are separate. With a circular queue, don't forget you need to circle round, so you can't just increment things like the front and the rear. You have to use the mod operation to get the right value when you're wrapping around. Don't forget to do the empty and full checks before you try and do anything on your queues and stacks. And don't assume that linked lists shift data around. They don't move any data, they just change the pointers. Okay, that's the end of 10.4 and the end of part 10.